Well, the reason why light never changes in its velocity is because the medium that which oscillates through doesn't change. It doesn't change in its nature.
It doesn't.
Whereas, depending on the temperature, how much air there is
It doesn't
in the
matter.
field, it would actually change the form of the medium.
Right, exactly. So it works a little different from sound waves in that way. This is not going to change according to temperature. It's always this. So that simplifies our work, right? All right, so, and we have different wavelengths. As Alex just pointed out, yeah, there are different wavelengths in color. Color, you can see at the bottom, and there's a little unit that they're using. Zach, what's the unit for color? I don't see meters anymore. What do they have there? NM, you notice that? Nanometers. Can you find that on the page somewhere? The color wavelengths are marked in nanometers. So that will be a pain because look at the unit for light, meters per second, or the speed of light. So we're going to have to switch nanometers to meters. So I wanted to remind you from what day one when we made our ladder of units. Yeah. It was 1 meter equals 1 times 10 to the minus 9. All right, so 1 meter, or let's say a nanometer, sorry. A nanometer is 1 times 10 to the minus 9 meters. That's the equivalency that we're going to have to use when we switch nanometers from nanometers to meters. All right, so another way we could say that is there are 1 times 10 to the 9 nanometers in 1 meter, either way. So let's do a problem there. Is there room somewhere? I didn't have a lot of room on there. If you could get maybe beside the electromagnetic, yeah, there's room on the back, or maybe beside the electromagnetic wave, but if you've already written there, find a spot. Let's say, and here's another change that we often have. Let's say we have a frequency of light, and get some room here. Keep this up. So I'm going to give you the frequency of the light, and I'm going to ask you to find the lambda, the wavelength. So the frequency of the light I'm going to give you is 1100 or 1120 kilohertz. So that's another difference because we're working with these light. Nanometers is going to show up and so is kilohertz. So in order to put it all together and come up with regular hertz, we're going to switch this to regular hertz. So how many, MD, how many kilohertz, how many hertz do you think is in a kilohertz? 1,000. Kilo is always 1,000. So we can change that pretty quickly by just moving the decimal, adding 3 zeros there. So that is nice, and the metric system is sweet to us. So I'm going to add 3 zeros. So I end up with 1,120,000 hertz. So we're going to have to switch it right away. So now we're set to find lambda. So this is the number, 1,120,000 goes in for frequency. Velocity, we already discussed, is always 3.0 times 10 to the 8th meters per second. And then you solve for lambda, the wavelength. So go ahead and do that for me. Pretty long wavelength. Are you coming up with one that's fairly long? Anything on your screen yet? So for the frequency is 1,120,000. That's our F.
Should we stop the video? What time did we start? 7:54?
Velocity
7:33.
over lambda. Mathematically, you're going to end up dividing this number by this number. So what are you getting? Zach, you got something?
Is it really big?
Oh, it's fairly big.
I got 3 million.
No. Are you dividing
That's
this?
what I got.
I got 3.73.
I got 268.
point oh oh
I
three
didn't mean to
seven.
right.
Are you doing this number divided by
Miss
this
Powell?
number?
Yeah.
Miss
so I
Powell,
got
we need to
268.
stop the recording.
268 is what I got.
No, not yet. It's fine.
Okay.
What?
Okay,
268.
so it's been
68.
14 minutes.
268.
Oh, 268.
Dang.
Yes.
13.
Boom. She had to divide it. Just divide. Oh, you're like, going to calculator. I was like, you want to see for yourself?
All right, 268.
No, how did you put it in?
And because we're using this value for light, it's only 2 significant digits. It is not infinitely significant, so we're going to bump it back to, or up to 270. So why are you all getting these weird numbers, Zach?
You know, I tried to do something that I thought might work.
Okay. Do you remember how to use the EE button?
Oh,
That
yeah.
helps. If you
Yes,
put
I
in 3.0, second function, what's the EE button above?
It's still comma actually.
Above the
Yeah.
comma, second function, comma, 8. Then you don't have to worry with parentheses.
Yep.
And that's divided by this. Alright, so it should come out to about 270 meters, which is a pretty long wavelength. So the distance between wave crests was 270 meters in that problem. So if we're seeing this on our screens from double slits, we're using this formula and it's working, this all indicates that light is a wave. Enter Albert Einstein. And he noticed some oddities about light that he could not explain as a wave. And so he rocked the scientific and community by presenting them. So they're kind of hard to write them all out. So if you turn your paper over, I think I wrote them on there for you. Did it come through? Those 4 things? All right, so
Who was the first guy you mentioned?
his name was James Maxwell. He said light was a wave, and he had a lot of support behind what he said. So it made sense. It made total sense. So, however, this is some of Einstein's less known work, but it is really important work. But we don't hear about it as much.
We can start, I think, it's
Yeah,
15
okay.
minutes?
Could you shut that down too? And what were you gonna say?
It's 15 minutes, right?
Yeah.